All right, let's talk about some basics of thermodynamics. Two main laws to consider. Things you already know: energy is conserved, and it always moves from hot to cold. Now, this second law goes a little bit deeper, that entropy always increases, but there's other videos that'll go deeper into that. Take a look at the arrow of time later on in the playlist. But energy is conserved. When we're talking about energy, we're talking about thermal energy. We're talking about thermal energy. We want to know how fast are those molecules moving. They have kinetic energy. Now, the average molecular kinetic energy, the average that each one individually has, that is related to temperature. So we can start talking about temperature if we start talking about, okay, how fast are those molecules moving on average? Not all of them are moving the same speed, but on average, how fast are they moving? So a couple different ways we can measure that. You have Celsius, you have Fahrenheit, which are really arbitrary points to put 0 degrees. But really, to be fair, we want to usually look at Kelvin, because we can all agree that there's an absolute 0, no more molecular motion, all the way down there when all that motion stops. So when we look at a change in temperature, though, Kelvin and Celsius are pretty much the same size degree. We just moved it back 273 degrees. Fahrenheit has its own absolute temperature scale called Rankine, and you can look that up if you're so interested. Basically, you move things over negative 460 degrees. All right, so that's molecular motion. Most importantly, it's always moving from hot to cold. How can it do that? Well, three ways to transfer: conduction, convection, radiation, things you've already talked about. So conduction, you actually have physical contact. Two substances need to be physical contact, and energy transfers one to the other. Convection, you actually have moving fluids, so boiling water, wind. If you have a fan in a room, that moving air can transfer energy, and also radiation through electromagnetic waves. Now, we're going to look at conduction and radiation in two separate videos, but first I want to talk about energy transfer in general. So, you're hungry, you want some ramen, you need it fast because you're super hungry. So you can either choose a stove and a small pot with a small amount of water, or a large crock pot and a candle. Now, this is not super unobvious. You want to cause a temperature change in the ramen. You want to cook it, but you have a very large amount of energy here, very small amount of mass, and it's made of metal, which is really easy. It's really easy to heat up. It has a small specific heat capacity. The crock pot, however, has a very large mass. It's a crock pot. It's made of porcelain. It's very difficult to heat up, but it will retain that heat for a long time. And it's a candle, so you can only add a very little amount of energy. What's going to change temperature most often? Now, obviously, you're going to pick this scenario over here. Why? Because that change in temperature depends on the amount of heat that you add, the quantity of heat added, how much mass you're trying to heat up, and the specific heat capacity, as in how easy is it to heat, the thermal inertia, if you will. Now, we can make this an actual equation, and we start thinking about the units that we use. So let's think about this. If we want our change in temperature to be Kelvin or Celsius, all these units have to agree for everything. And a lot of it will be determined by your specific heat capacity. It's going to be given to you in either calories per gram degree Celsius, or joules per kilogram degree Celsius, or joules per gram degree Celsius, or whatever this says. Make sure if this is in kilograms, that's in kilograms. If this is in calories, that's in calories. Right? Just make sure they agree. But if you have everything in the right units, that should actually make this an actual equals sign. Now, one last thing to consider. Zoom back out. Let's say we put our ramen back in the actual pot. And all right, now we have our ramen in the pot. Let's think about where the energy is going. Energy is transferring from the water to the ramen. So as the water transfers that energy, we have two energy transfers going on here. The water is actually, let's put the water in blue. This water is losing energy, right? But the ramen is gaining that energy. Well, guess what? Those have to be the same. The energy that the water loses is the energy that the ramen gains. If that's true, that becomes very useful, because we can then look at the mass and specific heat capacity and the temperature change of the ramen and set that equal to the mass times specific heat capacity times the temperature change of the water. And now that lets us find final temperatures, lets us solve for a mass, but it becomes very powerful. All because energy is conserved. Whatever energy is lost by something is gained by something else. All right, so zooming out, looking at the big picture here. First law, energy is conserved. Second law, always going from hot to cold. Entropy has to increase. Oh yeah, by the way, they threw in a zeroth law as an afterthought because they realized they had to establish that if two things are in equilibrium with a third thing, the third thing is equilibrium with the second, with the first. Everything's in equilibrium with each other. But no energy is transferred if everything's in thermal equilibrium all at the same temperature.